Okay, now we're going to be looking at the electromagnetic wave relationships. All right, so electromagnetic waves are represented by this equation, C equals lambda V, where C is the speed of light, 3.10 times 10 to the 8th power meters per second. Wavelength is lambda, and frequency is the V. This equation represents this relationship, and we use this because the speed of an electromagnetic wave is a constant. It never changes in air and in a vacuum. So because we know the speed of light, we can use this equation to determine unknown wavelengths and unknown frequencies. This should be pretty familiar if you've had physics. This is something that you learned in physics. Now, a quantum is the smallest amount of energy an atom can gain or lose, and this should look kind of familiar. So the energy of a quantum is set up the same way, except that on the left side, instead of speed, we have energy measured in joules. And on the right side, we have Planck's constant, which you should have looked up for your vocabulary, and the frequency. So Planck's constant is 6.626 times 10 to the negative 34th power joules per second. So joules is a capital J, right? And then the little dot means times or per, and then second is S. So Planck figured out that atoms can only gain or lose energy in certain specific amounts, and they can't lose it in other like fractions of that amount. And so he came up with a constant that allowed us to calculate that. Now, what's really cool about that is that the energy of a quantum is the same as the energy of a photon. So since waves of electromagnetic energy can behave like a particle, we can also use this to represent the particle nature of light. So the energy of a photon is E photon, also measured in joules. H, of course, is Planck's constant, and V is the frequency again. So because a photon has the same amount of energy as a quantum, certain materials like metals that easily lose electrons have a unique reaction to being struck with very specific frequencies of light, and this causes them to actually release those electrons. This is the photoelectric effect. So if you strike metals with specific frequencies of light, they actually release electromagnetic radiation, which is really cool, but very unusual, and it's usually just metals that do this. So how exactly are we going to use these? Well, one way that you can use this is you can use this to figure out what the energy of a photon is and whether or not that energy is going to meet the requirements to release an electron from a specific substance. So if a photon has a frequency of 7.230 times 10 to the power 14 hertz, what is the energy of the photon? Remember, seconds to the negative first power means hertz. So the first thing you're going to do is write out the equation in words. E photon equals hv. Then you're going to write what you know and what you don't know. So your knowns are your frequency and Planck's constant. Your unknown is the energy of this particular photon. Now you're going to replace your known values in your handwritten equation, the one that's all words and symbols. That gives you E photon equals 6.626 times 10 to the negative 34th power joules per second times 7.230 times 10 to the 14th power hertz. Okay, now I chose to write the hertz as seconds to the negative first power because it makes it really obvious how you cancel the units. Now you're going to multiply your coefficients, add your exponents because you're multiplying in scientific notation, then there we go. My headset went dead. Then you're going to cancel out your units, seconds and seconds to the negative first power cancel. And then you're going to put it all together, and it gives you 47.906 times 10 to the negative 20th power joules. Now, I will take this answer, but if you wanted to fix this and make it proper scientific notation, which I did not do here, you would put in 4.7 906 times 10. And because we went to the left, we're going to we're going to add 1 to this, so it actually makes it negative 19 joules. Okay. I'll see you in the next lesson.